In the last video lecture, we talked about this theorem, and I mentioned that I will give you an example of how to use this theorem in a particular case. Now remember that this video is part 2 of a sequence of 2 videos that the main purpose is to describe what are the generators of a finite cyclic group. Alright, so let's recall the theorem here. So the theorem says that if you have an element of order n in a group, then you can find the order of any power of that element by using this formula, n divided by the greatest common divisor between n, the order of the element a, and k, which is the exponent here. So let me give you an example. Let's say we look at this group. So let's consider this group U22. This is a group we talked about it before, and let's recall what it is the collection of all the natural numbers that are less than or equal to 22, and the greatest common divisor between that number and 22 is 1. Now this here is the formal definition of that set. You can describe it in words by saying that is all the elements from this collection from 1 to up to 22 that are relatively prime to 22. So that's why you put U22 here. You can do the same thing for any other number here. So that is a set. Now to make it a group, you have to give it a binary operation. And the binary operation that we have on this set, U22, is multiplication modulo 22. So what I mean by that is the way you operate two elements in the group A and B is you multiply them as you usually will do with just numbers, and then take modulo 22, which is the remainder when you divide it by 22. Now what are the elements of U22? So all the relatively primes to 22, all the numbers that have the only common divisor with 22 is 1. So if you want to double check, these are the list of all those elements. So it's 1, 3, 5, 7, 9, 13, 15, 17, 19, and 21 are the elements of U22. Now 1 here will act as the identity for this group. Now we can check that the order of 3, which is an element of the group here, is 5. Now how do you check that? You'll have to check that 3 to the first power is not the identity, second power, third power, and fourth power, all of them are not the identity, which is 1 in this case, and 3 to the fifth is the identity. Now remember, this notation here means you operate the number 3 with itself twice, and that operation is always modulo 22. So when we write down 3 to the fifth, that means 3 to the fifth, and then you take modulo 22. So you get 1 in that case. You can double check that that is the case. So in this particular case, the element 3 has order 5 because it's the first exponent for which you get the identity, or the smallest natural number for which you get the identity. Okay, so let's say we want to apply the theorem. So let's say we want to find the order of 3 to the 20th power. So how do we, 2 to the 11th power. So let me erase that here. So the one that we really want is to the 11th power. To the 11th power. So let's look at that. So what would be the 3 to the 11th power? So by the theorem is going to be n divided by the GCD between n and k. But what is n in this case? N is the order of the element here, the order of 3. And k is this exponent. So in this case, in our case, n here will be 5, so it's 5, and k is the exponent 11, which is this one right there. Now the greatest common divisor between 5 and 11 is 1, so we get 5 over 1, and that gives us 1. So the conclusion from the theorem is that the order of 3 to the 11 is also 5. So this corollary talks about the order of elements in a finite cyclic group. So basically what this is saying is how the order of an element is related to the order of the group. So let me state the corollary first. So we have a finite cyclic group. So it's important that it's finite and it's cyclic. And let's suppose you take an element x in G. Now, two important facts come out of this, assuming that the cyclic group is finite. One is that the element has to have finite order. And the second, and probably the most important property, is that the order of the element X has to divide the number of elements of the group G. Remember that these bars here with G means order. It depends on the context. The bars here, bars of a set, is number of elements. And when you put bars around an element means order. So X has finite order, and the order has to divide the number of elements in G. Alright, so let's look at the proof. So to prove this, of course, we have to assume that we have a finite cyclic group. And let's take an arbitrary element of G. So let's prove number one. So I have to prove that X has finite order. The way we're gonna go about the proof is by contradiction. So we're gonna assume by contradiction that X has infinite order, so the opposite of finite order. So let's suppose that X has infinite order. Now what that means, and that will imply that if I start taking this, if I look at the set of all the integer powers of X, which is this one, the identity X, X to the negative 1, X squared, X to the negative 2, this here is gonna be an infinite set. Why is this like that? Because imagine that if this was not infinite, that means there would be two different powers with the same value. That will imply that the element X has finite order. So in this list, all the elements are different. So that means that that is an infinite set. Now, if you're not convinced about what I just said there, just do a little proof about that. So if two elements here are the same with two different exponents, that will imply that X has finite order. Okay, so assuming that we have this, that this is an infinite set, so let's continue with the argument. So we know that this is closed under the binary operation. So all these elements that are here in this set, all these elements will be elements of G. And that will imply that this collection, the collection of all the powers of X, are included all in the set G. But there's a little problem here. The problem is because we are assuming that X has infinite order, this set will be an infinite set. But this is sitting inside a set that is finite. And that's not possible. You cannot have an infinite set included in a finite set. So that would be the contradiction. And the contradiction is what I just described here, that an infinite set cannot be subset of a finite set. So what that means is we have proved that X has to have finite order. Now that's only the part number one. The second part is we have to prove that the order of the element has to divide the number of elements of G. Okay, let's go to the proof number two. By the proof we just did, the part one, we already know that X has finite order. So let's say that that order is n, some natural number n. Let me call this number one. We know that that is the case because we already proved that X has finite order. What we need to do is we need to prove that the order of X or n divides the number of elements of G. So that's what we need to prove. So let's go about the proof here. So this is how the argument is going to start. So we know that this is cyclic. This is by the general hypothesis. If it's cyclic by definition of cyclic, that means that there is an element of G, so that G is all powers of that element. This is just the definition of being cyclic. Now G is also finite. That is also part of the general hypothesis. So that means that the number of elements of G is equal to the number of elements of this set, because they're equal. And remember, we have proved that the number of elements of this set is equal to the order of the element A. That all is true because we are also assuming that G is finite. So I just mentioned that here. We have proved this result in previous video. That's video number one. This is part two. That was proven in part one. So these all are numbers who are equal. They are just natural numbers because it's counting the number of elements in a set or the order of an element A. So let's put that, and let's say that is L. All right, so L here will be actually the order of the generator of the group G. So what we can conclude from all of this is that the order of A is L, and L is also the number of elements of the group G. So let's call that number 2. Now, we have to show that X, the order of X, divides L, or divides the number of elements in G, which is exactly the same. So how do we do that? Now, one thing that we can use is that X is an element of G, so X itself is a power of A, because all the elements of G are powers of A, a power of some integer exponent. I'm going to call that number 3. So X has to be an integer power of A, because G is cyclic with generator A. Then let's look at this. So we know that n is the order of X. We just using the notation that n is the order of X. This is by number 1. Now X is also a power of A, which is by number 3, that is here. And we prove we didn't prove a theorem, but actually we are assuming that theorem without proof. We can check the proof in the book, that the order of any power of A is the order of the base divided by the greatest common divisor between this exponent and the order of A. So here I'm using the theorem that we saw in the last video lecture, and also the one we used at the beginning of this video. So we are using that theorem. So we have this. Using all these inequalities here, so that means that this n is equal to this expression that we have here. So n is equal to this. Now, we can take this and we can rewrite it like this. How do we do that? Just multiply on both sides of this equality by the GCD. So then L will be n times this GCD. Now, if you look at this last equality that we have here, what this actually means is that L is a multiple of n, because this here, the GCD between m and L, is actually an integer. So that means n divides L. And L is, of course, the number of elements in G. So we have proof that n divides the number of elements of G, and remember, n is the order of X. So that will prove part number 2. So we have just proved the corollary. Now this is an important corollary because let me scroll all the way back to the statement. The statement here, the most important part is that the order of X divides the order of G. Now that's gonna put a restriction on what possible orders X could have, depending on the number of elements of G. Let's say, for example, you have a group of 20 elements. So if you have a group of 20 elements, the possible orders of an element in G can only be divisors of 20, if this is 20. So that puts a restriction. So for example, if you have a group of order 20, you cannot have an element in G that has order, for example, 3, because 3 does not divide 20. So that puts a restriction on what orders you can have on elements of a finite cyclic group. All right, so let's look at the next corollary. Remember, all of these corollaries and results as all preparation to give an idea on how the generators of a finite cyclic group are. Okay, so let's look at the next corollary. The corollary is a criterion on when two subgroups of this type are the same when they are generated by powers of the same element, the ith power and the j power of the same element, and when the orders of powers of the same element are the same. So let's look at this corollary. So the statement will go like this. So let's say you have a group and you take an element of G, and we're gonna assume that element has finite order n, This n, of course, has to be a natural number. Now, when will these two sets or subgroups be the same if they are generated by powers of the same element? So that's all going to depend again on the exponent. So how are these going to be the same? They are the same if and only if the GCD between n and I, n is the order of a, n and I is the same as the greatest common divisor between n and j. So these two subgroups are the same if and only if, so equivalent to say that these GCDs are the same. And a similar conclusion happens if you compare the orders of the elements. So an order of a to the I is equal to the order of a to the j if and only if the GCDs are the same. The GCDs with n are the same. All right. So let's look at the proof of this corollary. So the general hypothesis is that we have an element of a group that has a finite ordered n. So we assume that A is in G and A has finite ordered n. I'm going to call that A. I'm going to label it A. So I'm going to prove number one. Number one is an if and only if statement. So what that means is I have to prove this if and only if statement, I have to assume that this is true and prove that this statement is true, this one here, and the other way around, assuming that this is true and proving that this is now true. So we're going to go in this direction as first, assuming this is true and then proving this one. That's what this arrow here means. So I'm going to assume that the subgroup generated by a to the I is equal to the subgroup generated by a to the j. Now, if they are the same, that means that they have the same number of elements. And so that's what this means here. Number of elements of this set is equal to the number of elements of this set. I'm going to call that B. Now we're going to use the corollary that we proved in a lecture before, that is this one. The order of an element x is equal to the number of elements of the subgroup generated by that element x. So we're going to use that in B, in this one here. So applying this to B, then we get this, that this here, the order of this, or the number of elements of this set is equal to the order of a to the I. Exactly the same for this one. The number of elements of this set is equal to the order of a to the j. So that's the conclusion we get here. That's let's label this one C. Now, again, using the theorem from that we used at the beginning of this video. So from the theorem, we can find the order of a power of a, knowing what is the order of a. So the order of a to the I is the order of n of a, that's n, and divided by the GCD between n and I. Apply the same theorem to this one, a to the j. So the order of a to the j is n, which is the order of a, divided by the greatest common divisor between n, the order of a, and the exponent that is here. This is actually here on j. So there's a j here. All right. So that's part D. Now, but if you look at C and D, so I can replace D into C. So if you do that, replacing C into D, because these two numbers are the same, but this number is equal to this one, and this number is equal to this one. So these two must be the same number. So replacing D into C, we get that n divided by the GCD of n and I is equal to n divided by the GCD between n and j. You can actually conclude from here that these two GCDs have to be the same. Why? Because we'll just do a little bit of basic algebra. You can just cancel out the n and just do the reciprocal. You will get that these two numbers are the same. So that proves the first part of part one, which is, let me scroll all the way back, which is assuming that this is true and proving that this is true. Now we go backwards. So we're going to assume that this is true, and then we're going to prove that these two sets are the same. So let's do that. So for that part, we're gonna assume, of course, the GCD of n and I is equal to the GCD of n and j. I'm gonna call that E. Now, also from my theorem that we described in the last video, part 1, this is part 2, the set or the subgroup generated by a to the I is exactly the same as the subgroup generated by a to the GCD between n and I, when n here is the order of this element. Now, we stated that theorem in the last video lecture. But the GCD between n and I is equal to the GCD between n and j. That's what we are assuming here. That's E. So that's why we can make this a step here. But the GCD between n and I, this set here, is equal to this one, applying the same theorem that we apply here. So what that would mean is that this set here, but this chain of equalities is equal to this one. So this shows that these two are the same set. So that proves number 1. That's part number 1. Now, proof number 2 is actually a little bit easier. And I'm not going to go into the details of that. I'm just going to give you an idea on how that proof is going to go. So the way the proof is going to go is like this. That's going to follow directly from the first part. The only thing you have to look at here is that what is the order of a to the I is the same as this order here. That's by a result we prove also in another video lecture, and this one is the same. So if you use part 1, you can use part 2 just by looking at this two equalities that are true by a theorem or a result we already proved. So if you don't know exactly how that proof goes, just sit down and think about it, and you will see that it follows directly from part 1. Alright, so finally we are ready to describe the generators of a finite cyclic group. So this is a corollary, and that's why I put this as important, because this is the result that tells us if you have a generator of a finite cyclic group, how you get the other generators of all the generators of the group. So let's look at the statement of this corollary. So let's suppose you have a group and you have an element of that group G, and you have that element has finite order n. And so this is what the corollary said. The subgroup generated by A is equal to the subgroup generated by a to the j. They are the same subgroup if and only if the greatest common divisor between n, which is the order of A, and j is 1. And the similarly, you take that the order of A is equal to the order of a to the j if and only if the GCD between n and j is equal to 1. Now, if you look carefully at this equality that is here, this is exactly what we're talking about. If you have a group that is generated by A, that group is going to be generated by a to the j only if this exponent here, the GCD between that exponent and the order of A, is 1. Now, the proof of this is going to be actually quite short, because this proof, the proof of the important result here, is going to be based on this corollary that we already proved. This one right here, this corollary. Take a look at this one more time, because this is going to be the part that we're going to use to prove the result we are looking for. So let me scroll all the way down again and look at the important corollary and how the proof is going to go. Okay, so we're going to assume that A is in G and A has order n. Now, if you look at these two here, and you instead of A, you put a to the first power, you see that these two results, these two things that are here, are exactly the same as the previous corollary when you take I equals to 1. That's what I say here. So assume that So you take I equals to 1 in the previous corollary, and you notice that the GCD between n and I is 1. So this is an I here, an I here, and then replace that I by 1 in this previous corollary, and then you will get the result. The GCD between n and j is equal to the GCD between n and 1. But what is the GCD between n and 1 is 1. So that's why you get GCD of n and j has to be 1, because this one right here is equal to the GCD between n and 1, and of course that is equal to 1. So that's how you get the proof of this corollary, just by looking at the previous corollary and taking I equals to 1. Now, if you still need to think about that a little bit more, go ahead and think about it, why that proof only follows by taking I equals to 1. So the proof of this one was actually very short. Why? Because we already prepared a lot of results before this one. Now, more importantly is this remark, which is going to use the corollary. So if you have a group that is cyclic, that is generated by A, and has order n, so the A has order n, or the group G has order n, what the corollary says is that any generator has the form A to the J, where the GCD between n and j is 1 when n is the order of this set, or the order of an element A, and n is the order of A, and j is an integer. So any generator of a cyclic group of order n, we have the form A to the j, with this j here is an exponent that is related to n in this way. The greatest common divisor between n and j is 1. Now, there's a lot of integers, of course, but you don't have to look at all of them. You can restrict the values of that j in this set. Why is that? Because if you look at the group G, which is all the powers of an element A, assuming that the group G has order n, then the group generated by an element A will have these many elements. We'll have a to the 0, which is the identity, a to the first, a to the second, up to a to the n minus 1. Because a to the n will be the identity again. So all the generators of this group have to come from here. If all of them have to come from here, they have to be of the form a to the j, and this j must be one of these exponents. So it could be 1, 2, or so on up to n minus 1. So you only have to check the elements of the form a to the j, where j is one of these exponents, 1 through n minus 1. So that's the important remark about that corollary. Now, in the next video, I'm going to talk about some applications of this theorem. So this couple of lectures or videos that we covered in this course so far was all to prove this corollary. In the next video, we will talk about applications of this, and you will see how you get the generators of some finite cyclic groups. Alright, so that is all I have to say for this video lecture, for this topic so far. Take care and good luck.